we have this Fibonacci sequence. We could square each number in it, and what we get is 1 square 1, 1 square 1, 2 square 4, 3 square 9, so on and so forth. If we add the square of the first n terms together, we would find that 1 plus 1 plus 4 equal to 6. 1 plus 1 plus 4 plus 9 equal to 15, so forth. When we continue adding, we discover that 1 plus 4 plus 9 plus 25 plus 64 is equal to 104. What's the relationship between these sums and Fibonacci numbers? We may not be able to discover it now, but if we convert the right side to the product of two integers, we will find that 6 equal to 2 times 3. Then let's see, 104 is equal to 8 times 13. So actually, all the right-hand side are equal to the products of two adjacent Fibonacci numbers. So now, could we find an identical equation for it? This means for f1 square plus f2 square and add to fn square, which is a term sum of squares of Fibonacci numbers, is equal to the product of two adjacent Fibonacci numbers, which is fn times fn plus 1. Is this equation correct? It seems to be correct by checking these four equations. Now let's prove it. And first, how should we represent one square? We could use a square with silence 1 to represent it. So we could think that, for example, 1 plus 1 plus 4 is to put two 1 by 1 squares together, and then add a 2 by 2 square, which is a little bit larger. Now we construct a 3 by 2 rectangle. Then if we add a 3 by 3 square besides it, then we could add a 5 by 5 square, then a 8 by 8 square, and so forth. So what do we find? This is the last equation we just listed. 1, 1, 2, 3, 5, 8. The quadratic sum of all these numbers should be equal to the area of the big rectangle. What's the area of the rectangle? Its height is Fibonacci number 8, and its length is Fibonacci number 5 plus 8 equal to 13. So we'd find that by combining these squares and rectangle, finally we get a rectangle whose area is the sum of areas of all small squares. And the area of the big rectangle is actually the product of two Fibonacci numbers. The sum of area of all small squares is the quadratic sum of these Fibonacci numbers. So this time, we successfully proved a Fibonacci identity without using a single mathematical symbol. Actually, if you are searching on the internet, you'd find that there are a lot of information about the proofs without words. We just use a proof without words for Fibonacci identity. So we might think, is there a proof with words? Could we prove it by logic deduction? Let's analyze it carefully. Let's prove such an identity that f1 squared plus f2 squared plus n2 plus fn squared is equal to the product of adjacent Fibonacci number fn times fn plus 1. Now we could think that every fn satisfies the recurrence relationship. So fn equal to fn minus 1 plus fn minus 2. So among these squares, could we pick one term to manipulate? For example, let's give such a proof. For f1 square, as both f1 and f2 are equal to 1, f1 square could be written as f2 times f1. For f2 square, let's keep it one of them. For the other f2, by the recurrence relation, f2 equal to f3 minus f1. Now let's multiply them together and get f2 times f3 minus f2 times f1. Now we could see that there seems to be a change in index. Then f3 squared could also be written as f3 times f4 minus f2, which is f3 times f4 minus f2, f3. Now, if we add them together, we discover that here is f2 times f3, and there is another f2 times f3. By adding them together, they will be eliminated, so forth. We will discover that when adding to the last term, fn squared is equal to fn times fn plus 1 minus fn minus 1. After simplified, it becomes fn times fn plus 1 minus fn minus 1 times fn. Then let's add them together. We get the left-hand side of an identity. For the right-hand side, we discover that f2 times f1 and f2 times f1 are eliminated. f2, f3, f3, f4 are all eliminated. Only the last term, fn times fn minus 1, is remained. So after adding them up, we get the equation f1 squared plus f2 squared plus until fn squared is equal to fn times fn minus 1. So we discovered that this recurrence relation could help us to prove Fibonacci identities. Then let's continue. Well, let's look at such an identity. f1 plus f2 until fn is equal to fn plus 2 minus 1. We could see that the sum of the first n Fibonacci numbers is equal to fn plus 2 minus 1. With the experience we just gained, we know that we could write any Fibonacci number as the difference of two Fibonacci numbers. With such an idea, let's say that for instance f1 could be written as f3 minus f2, f2 is f4 minus f3, so forth. fn equal to fn plus 2 minus fn plus 1. With this equation, we discovered that we could get something by adding them together. For example, here f3 and f3 could be eliminated. f4 could be eliminated. Finally, fn plus 1 and fn plus 1 are also eliminated. The only term left is fn plus 2 and f2. So the sum of the left-hand sides are exactly f1 plus until fn. Right side is fn plus 2 minus 1. With this idea, we could also prove the other equations. For example, f1 plus f3 plus f5 until f2n minus 1. This is actually a set of Fibonacci number with odd indexes. Their sum is exactly equal to an even index Fibonacci number, which is f2n. How should we prove it? The idea is exactly the same as the last one. For example, f1 equal to f2, f3 equal to f2 minus f2, f5 equal to f6 minus f4. So forth until the last term, f2n minus 1 is equal to f2n minus f2n minus 2. We could add them together, and we discovered that after adding them, the left-hand side is the sum of the all odd indexed terms, and in the right side, f2 and f2 are eliminated. f4 and f4 are cancelled. So forth, there are only one term left, which is f2n. So the left-hand side is sum of these odd indexed terms, and the right side is f2n. Now, let's think that there are a lot of such identities for Fibonacci numbers, and it has great properties. And could we calculate the value of a Fibonacci number fn? Is there a direct formula?